fields with exactly one complex plane.
So first, I'd like to thank the organizers for inviting me to speak. Very honored to be here. So this talk is about a preprint that went on archive 2 weeks ago and is a follow-up talk on Pierre Charolois and Luis's talk from yesterday. And we're going to try to adapt their construction to higher degree fields with exactly one complex place. So in the language of rank 1 Stark abelian conjecture, you may call this as ATR fields or almost totally real fields. And to do so, I first need to introduce the higher degree functions that we are going to use that look like the theta function and the elliptic gamma function from yesterday. And so that's what we're going to do first. And then I'm going to show you how we can adapt the construction that was presented yesterday by Luis to higher degree ATR fields. And if I have time at the end, and I hope I have time at the end, I will show some computations for higher degree fields, and maybe we're going to have time to go for a degree 6 field. So recall the theta function of yesterday. Nothing has changed since yesterday. This is the theta function you might use to produce elliptic units. And then there is the elliptic gamma function, right? And the elliptic gamma function, well, what did we do to produce it? We had another parameter. We had z tau, and now we have z tau and sigma. And then we transformed the product to a quotient. So to go further than this, we're going to add variables at each level if you want. And then we're going to transform products into quotients and then quotients back to products and so on and so forth. So this leads to the following definition. So this is the GR functions of Nishizawa. So you have a product that looks like the theta product or the elliptic gamma product. And we, at each level, we have added one more elliptic variable, and we have transformed the product to a quotient or the quotient to a product. So these are meromorphic functions, and they converge in a specific set. So we're going to look at elliptic variables in the upper half plane, obviously. And these functions are holomorphic in the upper half planes for these elliptic variables. And then they also are meromorphic in Z, which is the upper variable. And you can see the set of poles and the set of zeros is very clear from the definition. It's quite straightforward.
Can you slow down a bit?
I won't slow down, but as I only have 30 minutes, I won't.
We only have 30 minutes for 44 slides. Okay.
So
Yeah,
I
go,
have to be a bit
yeah,
compact.
go fast. Yeah.
So I just want to say, I think we're just adding one elliptic variable at a time. These are not really complicated functions. And one thing that we use all the time to compute is this expression. So simple sum, the exponential of a simple sum, involving sinuses or cosinuses, if you will. I saw that some people here are doing polylogarithms. And so if you want to think of this as a polylog, it's a polylog. And if you are not convinced that it's a polylog, in mathematical physics, they do something that they call elliptic deformation all the time. And this should be the elliptic deformation of a polylog. So this also converges as shown yesterday by Luis for arguments that are in the lower half plane, and we use this formula to extend the GR functions to the lower half planes for the elliptic parameters. And this is the formula that we use all the time to do this, if you want. It's a very simple formula. Now I'm going to review the properties of the GR function. So I'm going to show what it is for the theta and gamma function, and then for the GR functions. What I should have mentioned, and that was written somewhere, is that theta is exactly the G0 function, and the elliptic gamma function is the G1 function. So what's really new here is G2, G3, and so on. So first properties is that they have to be periodic in all their arguments, but this is quite straightforward because these functions are given via Fourier series expansion, Fourier products. So they are periodic with period 1 in all the arguments. The other thing that you saw yesterday is that these functions should be pseudo-periodic with respect to their elliptic parameters. So this is the pseudo-periodic relation for the theta function. And then for the elliptic gamma function, it involves the theta function. And then in general, the GR function has a pseudo-periodic relation involving a lower degree function. Now for the rest of the properties, there are simple properties which are not very important here, but we use also over time. And these are the transformation properties under the two involutions of C that we have. What happens when you take the minus sign everywhere, and what happens when you try complex conjugation everywhere. Now, the most important property for us is what we call the modular property, and this is what will give us the cocycle property at the end. So this is what was already written by Luis yesterday, the modular property for the theta function, with a very explicit polynomial, as you can see. It has a bit of tau in the denominator, but not so much, okay? And you see that the coefficients are Bernoulli numbers. So to get the exact polynomial for the GR functions that I have to use for the modular property, I need to introduce Bernoulli polynomials from Narukawa. And this is the definition by the generating function. And it's totally explicit as a sum of polynomial with Bernoulli numbers as coefficients and maybe factorial somewhere. I'm not going to extend too much on this. The definition is there to give the modular property, and if you want to see more of this, you can find it in the preprint. What's important is that these polynomials are really polynomials in d+1 variables and of degree n. And what we're really going to look at is the diagonal polynomials. Okay. Now I'm going to shift a bit and I'm going to say that d is equal to r plus 2, because I want to relate, I want to have the R cocycle for SL r plus 2. And this is how the modular property can be expressed for the GR function. You see on the left, we have a product of R plus 2 GR functions, and then if you want, it splits a cocycle on the right. I'm going to say a bit more about the cocycle in a moment. But if you remember Luis's talk from yesterday, what he did is he said there was the elliptic gamma function, but what we really need to do is extend the elliptic gamma function to a set of geometric gamma functions associated to pairs of vectors. And so he did this because this collection of functions already existed, and then I had to give the collection of functions associated to the GR functions. That's what we're going to do now. So I'm going to present to you the GR functions. So yesterday we had two linear forms on a lattice, and today in a rank-free lattice, and then here we're going to have rank R plus 2 lattices, and then we're going to have to take R plus 1 linear forms. So I'm just repeating that we are going to take a lattice and we're going to fix a basis and then orientation and so on. And then I have this technical definition that is a bit interesting if you read the preprint because it's everywhere, but it's just a useful tool to give a definition of the geometric GR function that comes next. So think of this as computing the comatrix of a set of vectors. But your set of vectors is maybe not full rank, so what is the comatrix in this sense? That's what this definition tries to fill. This is quite a heavy definition. I'm not going to say so much about this, but what we're really, so this is a definition that is given in, that could have been given for the geometric elliptic gamma function, but that is in fact proven to be true. And then we take this as a definition in the general case, and we prove that it's independent of the choice we make. So we take R plus 1 linear forms if you want, and then we have to use duality, take a family that goes with it, and we compute a product in the dual space, your product in the dual space. And then we have to prove that this particular product is independent of the choice of dual family that we took. I think it's not so interesting to just put some heavy weight on the definition. I just want to show the properties, which are, I think, very meaningful. So the property is that this is a finite product of GR functions, and the product is indexed by this set, which is a very important set for our purposes. And so this set has a great, the size of this set has a great impact on computation time, but it also has an impact on the arithmetic properties that we think we'll get at the end. The other thing I want to say is that in this definition, I took a dual family, and then I tell you that in fact there's only one dual family that I like, and then we don't really care about the dual family. So we're not going to talk too much about this. Now, what do we want for these geometric GR functions? Well, we just want to copy everything that we did yesterday, or we want to copy everything that happens with the GR functions. So we want a modular property involving Bernoulli polynomials. And then we also want an equivariance property under the action of SLR plus 2z. And we want to get some form of cocyclical relation at the end. Okay. So this is just the Bernoulli polynomials we introduced. They are ad hoc, they are just introduced to fit the modular property. So I'm just put the definition here for people who want to have the full definition. It's just here to get the modular property. So the modular property is expressed as follows. So we can have a product of R plus 2 GR functions on the left. So this time geometric GR functions. And it writes the splitting of the R cocycle on the right, which is given by this Bernoulli polynomial, which I carefully cast aside. Okay. This is not very hard to prove. The only thing you have to prove is that in all these functions, they are defined as the product of a finite product of GR functions, but you have to just say that the finite product is taken over the same set. And then once you do that, you can use the ordinary modular property for the GR functions. Okay. So now for the equivariance, well, it's just playing around with the definition that is made to be equivariant, and you just show this kind of property, which resembles the properties that Luis mentioned yesterday. I'm not doing the semi-product with z to the r plus 2, but you could if you want, and you would have a similar statement. Okay, so now maybe for the most interesting part is how do we really write the cocycle? So we take these kinds of elements in SLR plus 2z. So take the product. This is quite standard in cohomology. And you just look at what happens when you try to write the coboundary of this. And you write the coboundary of this as the exponential of the Bernoulli polynomial on the right-hand side. This should be very familiar if you remember the talk of yesterday, where you had, well, here you had you had only one, no, you had two elements of SLR 3z. Now what do we do with this? Well, with this, we have to do the same computation as yesterday. So we have to put some arithmetic setting in this, because here I haven't talked about any field for now. So what happens is that I'm just going to copy the construction of yesterday. So if you feel a bit lost, try to remember that it's just the same construction as yesterday. So we need the exact same ingredients as yesterday. So you take your ATR field, you take modulus, which is non-trivial. There was the question yesterday about could it be trivial or not. Try to make it non-trivial. And suppose that the class field is totally complex. This is to fit inside the case of the stock conjecture, rank 1 abelian stock conjecture. And then we need an ideal B to represent a class in the class group, and then we need some smoothing to have better arithmetic properties. So here I just recall the stock conjecture in the ATR case, rank 1 abelian stock conjecture, which I found in a note by Gupta here. And so we try to create units that resemble the storic units. This is what was done also yesterday. So I want to evaluate this cocycle as we have done in the cubic case. And so I need to know what I have to feed inside this cocycle. So I feed the same thing as yesterday. But the thing is now I have the group of units is not has not rank 1, it has rank R. So there's a bit more things to do. So I'm going to need a lattice and then an orientation form on the lattice and then an action of SLR plus 2Z. So I'm going to fix the lattice and a basis and everything so that everything is set. Then I need some elements in SLR plus 2Z, which are going to be related to the units. And then I need a base vector because this cocycle, if you want, has a base vector that I need to fit into it. And then I need the evaluation point W, and I need a linear form X, and it's going to be an embedding inside C. So here there's just technical details on the fact that we fix a basis on the lattice and we fix the orientation form. Then we have to consider this unit group that acts on the lattice and preserves it. So when I say epsilon greater than 0, this means that epsilon has to be a totally positive unit, so positive at every real place. And this unit group has rank R, and embedded inside SLR plus 2Z as an abelian subgroup once you have fixed your basis. So what we're going to do is we're going to fix a set of fundamental units for this unit group, and we're going to compute from there. Now I recall the definition of the geometric function. So you see this one more time, even though it's quite complicated. And what happens is that I see that there's a number gamma that appears, or an element in your field gamma that appears. But this gamma is related to the base vector A. In fact, I'm not going to say there's a one-to-one correspondence because you have to choose signs every time. So there's a correspondence up to sign. And this is what we're going to do. So instead of fixing A, base vector A, I'm fixing torsion point gamma. So here I recall that in the case of imaginary quadratic fields, you have to give the torsion points on the elliptic curves somehow. And here we also have to find an analog of torsion points. So this is the technical definition of admissible vectors we want to think of, and you can think of this as giving us the torsion points on something. Right. So we're going to fix this vector H, and then H has to be in the same line as gamma, and then gamma defines the base vector A. This is the technical definition of A from the vector H if you want, and then the technical definition of the vector gamma. And then there are two different products, or well, quotients that I would like to see. So these are smoothed GR functions. And then the thing is, I don't know yet the signs that I want to take. Is it plus A or minus A? I'm not sure. In the cubic case, if I take plus A or minus A, it doesn't change a lot. But in higher degree cases, it changes everything because I have to make a product of more values, as I will show in a moment. And these values, for some values I have to take plus A, for some values I have to take minus A. And for now, I don't know, I don't have a recipe on how to choose plus A or minus A in each case. So what happens with this last expression is that it depends very much on the choice of fundamental units you chose. So what you really have to do is to use the full rank R torus given by the units. So to do this, we're going to construct this product with parameterization by the symmetric group on R elements. So here I have some orientations. So the orientations mu tell you, do you choose plus A or minus A in the construction? And the orientations nu tell you, they tell you, should you take your element to the power +1 or -1? So we have to do maybe products, maybe quotients of things where we chose plus A, minus A. And there is only two good choices of orientations in the 2 to the R factorial choices. So it's sometimes hard to find. All right. So this is the main, we achieved the main function that we want to compute. And this is what we think is algebraic, okay? So first, before I state the conjecture on algebraicity, I just want to mention, so in this product, how many terms do we have to compute? So this is a product which is indexed by the symmetric group on R elements. And then you also have another finite product which involves a sublattice M. And now you don't really know what M is. So the base case scenario at least is to compute only R factorial terms. And this case arises when you have all sublattices equal to L. So in the preprint, I spend a lot of time explaining how to achieve this. So it's quite long. I do some algebraic number theory. I tell you how to achieve this, and I say, under these conditions, I can achieve this. This is a small product, and it's supposed to be algebraic. And this is the a part of the full conjecture if you want. Under the conditions in the preprint, you will find that this is a small product of only R factorial numbers, and it should give you the values of the derivatives of the zeta function at 0, as expected for the Stark units. And it should also be an algebraic number in an abelian extension of K, which should be well controlled. And it's just a bit technical where these numbers are. What you could remember is that if you take a smoothing large enough, so if you take n large enough, then you always happen to be in the ray class field of modulus f. All right. So here I have a few remarks. So obviously this conjecture in the case r equals 0, I don't add many things to the theory of complex multiplication, and you get q units instead of units. In the cubic case, the Kronecker limit formula is obviously a theorem by Bergeron, Charolois, and Garcia. And we, in all cases, and in the preprint, you can state the conjecture more precisely. And then I just want you to compare with the Stark unit relation, and maybe I forgot something here. I think I forgot something. And lastly, before I try to do some computations, I want to talk about the compatibility condition. So in the cubic case, you do a product of 1 factorial elliptic gamma function. And it is quite degenerate because there should be a compatibility condition, but the compatibility condition is always true. So you don't see this obstacle, this natural obstacle to what you're trying to do. But when you go to quartic cases, quintic cases, and so on, you see that there's a compatibility conditions on the torsion points that you have to choose, because I have to choose R factorial torsion points that they have to agree with each other. And so that's what I'm writing here. In the quartic case, I only have to check 1 compatibility condition, and I'm done. If I do degree 5 fields, I have to check 6 compatibility conditions between my torsion points before I can think that my number is going to be algebraic. And then, because I'm presenting a degree 6 example in a moment, in the degree 6 case, I have 24 conditions to verify.
Can you say quickly what you mean by compatibility condition between these vectors?
So the compatibility condition, there is a natural obstruction from the choice of fundamental units you make to have the equality of the sublattice M rho to be equal to L. And so the compatibility condition is I want all the M rhos to be equal to L. So this is maybe the strongest form of compatibility condition. And we hope that there is a more loose form of this, which tells you that the different sublattices M rho, they cannot be so different from one another, and there has to be some kind of way to make them all agree with each other. So it's a bit vague, I know, but the best thing I can do for now is to tell you that it works when you have all M rho equal to L, strongest form of compatibility. And this is what I wrote here. The other thing I want to say is that if you have all M rho equal to L, this is the case where you have the least amount of computation to do. And this is obviously a good thing because computations can become quite hard very fast. Now, if everything works out correctly, I'll try to do some live examples. Okay. First on a cubic field. Here. You will see correctly, even if it's only just numbers and it's hard to understand what it is. So I'm going to compute four products. So I'm going to look at no, not this. Not this. Not. I didn't tell him anything. So this is with 200 digits, I think. And I probably going to get lower precision afterwards so that you can see quite clearly, but you saw that we compute things relatively easily. And then what you can do, so either you want to use algebra directly on any of these values, so maybe on this one. And I expect it to be a polynomial of degree 12. And here I get this one is the same as yesterday in Pierre's talk. And then if you're not happy with algebra because let's say it's a difficult tool to use, you can also try to identify the relative polynomial. So I did this yesterday. You get this relative polynomial for the extension. It's lower degree algebra or line depth to do, and it's a bit more precise if you want. And now for the cubic example, what I really want to do is I have a good example because that's when the magic starts to happen. So here I'm just defining some elements which I'm going to compute on. And then I'm going to compute this product. And this is in a quarter, so this has been computed using G2 functions above a quartic field. And if I want, I can try to go for arch depth. And then I hope this is 8. And I think I'm correct. You see, there's this form of pyramid of coefficients. So the more you go to the center of the polynomial, the higher the coefficients become.
What's the quartic field in this case?
What's the quartic field? Well, quartic field. Everything is broken. Quartic field in this case is this one at the top.
The polynomial is degree 8 over Q.
Yes, so it's a degree 2
extension
of the quartic field. Yes. So this is one of the simple quartic examples that we can find because it's one where the abstraction is very limited. Because I don't have so much time, I'm going to try to go rapidly the degree 5 and degree 6. So I have to this. It's going to be a bit long because he has to. So I have 6 products to compute. Each product requires 4 elliptic parameters and 1 non-elliptic parameter. And then at the end, I get this value that you can find in the preprint. And here I'm probably going to obtain a degree 10 polynomial above Q. And here it is. And this has very nice coefficients, and we're very happy with it. In the case of a degree 6 polynomial, the problem is that computations become quite hard because 24 conditions becomes okay. And so we still do the computation, all right? And then this one I'm never going to get with algebra, all right? I can say so. Probably it's going to be algebra of something with 24, but it doesn't look to get a correct polynomial because I don't have enough precision on my computation. If I had more precision, I would probably try to achieve a better polynomial for my value. But the thing is, I probably need 2000 decimals, and this takes very amount. So what I can do instead, and what I did instead, is try to find an expression of this number in the class field that we knew from other means. And then we found that the absolute polynomial this unit had should be this one, and it has very big coefficients. And this is degree 12 above the degree 6 fields. It should have been 24, but in most cases, when you have an even degree field and you try to compute Stark units, if the extension is not cyclic, the Stark unit tends to live not at the top, but in a sub-extension. And then with this degree 6 example, I think that's going to be all. And I think it's time.
Thank you very much. Okay, we have two 30-minute talks back to back, and so I think it might be best to reserve questions for the for after the second talk. So I think we should just move into the second talk now, unless people